Recursive Definitions in Structural Induction, Section 5.3. So recall that we had recurrence relations. They were sequences that were defined using previous terms. So a recursively defined function with domain non-negative integers had two key features. That is, it specified some number of basis steps and gave you a formula for getting to the next step that was somehow constructed using previous steps. So take, for example, the recursive function where f of 0 is equal to 3 and f of n plus 1 is equal to f of n plus 2. So let's find a formula for f of n and prove that it is valid. That is, that it's a true formula for it, a solution. So first, let's explore. Let's see what this table looks like using the recursive definition. And we can see that we get the sequence 3, 5, 7, 9, 11. And so just by exploring this table a little bit and looking around, we can see, okay, 3 plus 2 gets me to 5. 5 plus 2 gets me to 7. 7 plus 2 gets me to 9. So it looks like I'm adding 2 each step. 2n plus 3 is going to be my guess. But now let's show that this is actually the same, that this will give the same values as the recursive definition. We're going to do that using induction. So let's show the basis step holds true. The recursive definition tells me that f of 0 should be 3. Does that give me the same answer as my new formula? Sure enough, it does. So the basis step I've shown to be true. Inductive step. Our inductive hypothesis is going to assume that the formula for f of k, that is that f of k is equal to 2k plus 3, is true for an arbitrary integer k greater than or equal to 1. So in this case, I don't have a left-hand side and a right-hand side. I have two formulas, a recursive one and the formula I just created, 2n plus 3, and I'm trying to show that they're equal. So you can sort of think of those as stand-ins for my left-hand side and my right-hand side, but I'm trying to show that these two methods, the recursive one and the formula, will provide the same sequence. So I want to show that f of k plus 1 will be 2k plus 1 plus 3. So don't get that confused. That's not me saying when I plug k plus 1 into f, I will get 2k plus 1 plus 3, because that's what you do get when you plug k plus 1 into the formula. The question is 2k plus 1 plus 3 actually equal to what would be in the sequence, right? What the recursive definition would also give for f of k plus 1. So the question is on that equal sign. It's a little more hidden this time, but we're asking, does the recursive definition there on the left give me the same answer as the formula there on the right? So let's start with that fk plus 1. And I just told you that we can't just say that that is equal to 2k plus 1 plus 3, because that's what we're trying to show. So what can we say about fk plus 1? F of k plus 1. Well, if we can't use the formula, we can use something that we do know to be true, that is the recursive definition. The recursive definition is going to be true because that's how this thing is defined. So I know, based on the recursive definition, that whatever the formula pumps out had better be the same as f of k plus 2. Well, now I can use my inductive hypothesis. That is, I've assumed something about what the formula would tell me for f of k. That is, it tells me that f of k would be 2k plus 3. So the inductive hypothesis says that I can use the formula f of k equal to 2k plus 3. Well, a little algebraic manipulation will tell me that I can rearrange this. 2k plus 3 is the same as 2k plus 2 plus 3, which is the same as 2 times k plus 1 plus 3, which is what I stated the formula should be. Therefore, f of n is in fact equal to 2n plus 3. The formula and the recursive definition provide the same answer. Let's try another. Let's let f of 0 equal 4. So that's the defined first step. The recursive definition is going to be f of n is equal to the previous step minus n. So let's find a formula and again show that it's valid. We'll begin by exploring. What does the recursive definition tell me the sequence should be? The recursive definition tells me that the sequence is 4, 3, -1, -2, 6. Sorry, -6. And I don't know about you guys, but when I look at that, no guess is jumping off the page at me. So I'm going to need a different technique. And in this case, the technique I'm going to use is forward substitution. So now it looks a little more obvious, right? It looks like I'm doing 4 minus the sum of 1 through n. So I'm going to go ahead and use that as my guess. So it looks like 4 minus 1 minus 2 all the way through minus n, which I can write in a more compact form as 4 minus the sum from 0 to n of I. Well, sorry, where I goes from 0 to n. So let's show that this formula provides the same answer as the recursive definition. We're going to do that with proof by induction. The basis step, plug 0 in, you get out 4. Excellent. That's what the recursive definition provided as well, that when you plug in a 0, you should get out a 4. So the formula and the recursive definition match for f of 0. They start the sequence at the same place. The inductive step, we're assuming that f of k is equal to 4 minus the sum from 0 to k for an arbitrary integer k greater than or equal to 0. And we want to show that the formula holds true for k plus 1. So we're starting with what is f of k plus 1. Again, we can't assume the formula is true. We're trying to show the formula is true. So we're going to have to start again with the recursive definition. We know the recursive definition is true, so we can always state that 4k plus 1 should be equal to 4k minus k plus 1. Now I can use my inductive hypothesis. The formula for 4 of k, f of k is equal to 4 minus the sum from 0 to k by the inductive hypothesis. Well, let's just wrap that k plus 1 into the summation, and you get 4 minus the sum from 0 to k plus 1, which is what the formula was. Therefore, I've shown that the formula holds true. Note that we can write this a little more cleanly, right? We know that the sum from 0 to k plus 1 can be written as n times n plus 1 over 2. Oh, sorry, that's a typo right there. Let me fix that for us. This should be n. So let's try a couple more of these, and in particular, let's see if we can go the other way. Often what we're going to be interested in is taking a really complicated problem and cutting it down to size. So it can be useful to see this in the reverse, right? Let's take a formula and see if there's a way to recursively build up to it. Now, we won't do this often in terms of formulas, but in terms of approaching larger, more complicated problems that we have to program or that we have to solve with an algorithm, we're going to be very interested in seeing if we can chop this down to size into smaller, easier to handle pieces. So let's say we're given the formula a to the n. Is there a way we could have recursively gotten to that formula? So the key thing here is to note that the a sub n is the nth term in the sequence a sub n. So the notation is going to get a little sticky here, but a sub n is that nth term. Don't confuse that with a to the power n. So a to the power n is equal to, we can rewrite that, right? Factor out the a times n to a times a to the n minus 1. Well, a to the n minus 1 is the a sub n minus 1th, the a n minus 1th term in the sequence. So we can see here that this is how we can build our recurrence relation. So let's see what this looks like. All right, let's do that explore step with some numbers here. If you want to calculate 2 to the 5th, how can you do that recursively? Well, to find 2 to the 5th, you find 2 to the 4th and you double it. To find 2 to the 4th, you find 2 to the 3rd and double that. To find 2 to the 3rd, right, you find 2 to the 2nd, so forth and so on, until you get to 2 to the 1st, which we know is 2. So that's we work down to a base case there. Note that this is what it looks like working down. If we were going to actually do the calculation, we would start with our base case and work our way up. Let's see another example. Let's say we want to find a recursive definition for 4n minus 2. For this one, it doesn't jump off the page at me how we're going to do it, so I'm going to do a little exploration here. This is the sequence -2, 2, 6, 10, 14. And I note quickly that the difference in each of these is 4. So how do you get from one step to the next? You add 4. Starting at -2. Let's get a recursive definition for n times n plus 1. Again, I do some exploration, and this one is very tricky. 0 to 2, 2 to 6, 6 to 12. So it's not like I'm adding a set number here. Let's look at those differences though, just in case they reveal something. 2, 4, 6, 8. Well, at least those are numbers I'm familiar with. In fact, closer examination tells me they're double the n value. So that provides my guess. I'm going to guess that a sub n is equal to a sub n minus 1 plus 2n. And I can use the previous techniques we've mentioned to actually see if that is the correct answer.